Hello students, welcome to Sarasa classes. Now in this lecture we're going to discuss the general organic chemistry. So there are two types of effects. One is the permanent effect and the other is the temporary effect. Now under permanent effect we have four topics known as inductive effect, the hyperconjugative effect, the same is also known as no bond resonance, also may be known as Nathan Baker effect. Okay, and then we have at C the mesomeric effect, whereas in temporary effect you have two topics which are known as the inductomeric and electromeric effect. Okay, so what we're going to do, we're going to first discuss what is a inductive effect. Okay, so we are going to discuss inductive effect. What is it? We will say it operates when there is an electronegativity difference between two atoms wherein the most electronegative atom pulls the electron density away from obviously carbon atom, generating a partial positive charge that is delta plus on the carbon atom. So in other words, we will say inductive effect is always taken in the reference to the hydrogen atom. Okay. Besides, in organic chemistry, say if a atom or group pulls the electron density towards itself, or better to say, away from the carbon, via sigma bond, it is called the minus I group. Okay. So in other sense, we will say whenever we have a picture like this, that we have a C and we have a, say, group X, and it is pulling the electron density away from the carbon, then this particular group will get a negative charge and this one will get over here a positive charge. Okay. Besides that, this is a permanent effect. It is mostly seen in saturated molecules. How long does it operate? Operates till the chain length of 3 carbon atom So what can we say? That inductive effect loses power with increasing distance. So these are the key factors that one should remember while one is considering or learning inductive effect. Now, what is the order of inductive effect? Of, say, groups and atoms. So we will say for minus I effect, this is the order that it will follow. We have NF 3 plus greater than NH3 plus greater than NO2, which is greater than SO3H, greater than Cn, followed by CHO, then we have the carboxylic acid group, followed by the ester, NH2, the amide, then we have the fluoride, chloride, and we can see the inductive effect is decreasing as the electronegativity decreases. Then we have the OR followed by OH. Then we have the acetylenic bond followed by the phenyl group, which is followed by the ethinyl group. Okay. Now for the plus I effect, what is the order we will follow? So plus I effect will be considered for the group or atom that will push electron density within the covalent bond to the carbon. Okay. Now, for example, we can say this will be done by, in general, any alkyl group. Okay. Not OH, but O minus will be pushing the electron density towards the carbon. Okay. The carboxylate group will also push the electron density towards the carbon. So, if we compare the plus I power of groups, and anions, then one can say that CH2 minus will be having more plus I effect than NH minus, then O minus, followed by CO minus, and followed by the tertiary alkyl group. Then we have the secondary alkyl group followed by the primary alkyl group, which will eventually followed by a methyl and followed by hydrogen. Now let us compare or do some problems in relation to the inductive effect. So let's consider application of inductive effect. So straight away it can be used for predicting the stability of a carbocation wherein we will say stability of the carbocation will increase or directly proportional to the presence of electron donating groups, directly proportional to the plus I groups, and inversely proportional to electron withdrawing groups. Okay, or minus I groups. So over here, let's do some problems. So let me first list the problems. So we have a C connected to Me. Me indicates a methyl, and there is a plus charge followed by C, Me. Then we have a C, and we have a C. So out here, for this type of problem, we have to consider the plus I effects. So over here, there are 3 plus I effects coming from the 3 methyl groups. Here only 3. In the first one there are 3, but on the second one there are 2, and in the third one there are 1, and in the methyl carbocation there is none. So one that is having more plus I groups attached to it will be more stable. So the answer will be as follows. In question number 2, so out here we can see when the carbocation is over here, there are 3 plus I groups stabilizing it. When it is over here, there are only 2 plus I groups stabilizing it, that is alkyl arms. And over here, for this particular carbocation, that is a third, there is only 1 plus I group acting over it. So obviously the stability will be 1 greater than 2 greater than 3. Okay, in this case we have a CH2, then we have a Br, we have a F, so out here, higher the electronegativity of the group attached to the carbocation, less will be its stability. So when there is a fluorine attached in place of a chlorine, right, we will say it will be less stable. So over here, the stability order will be as follows. Okay. In option 4, okay, question number 4, it is the position of the fluorine that changes, right? Sometimes alpha, then in the next one beta, in the next one gamma. Now fluorine is what? A minus I group. That means it pulls electron density from the carbon. That way, if it is near, then it will be destabilizing more. If it moves far away, it becomes more stable. So that way, if you think, this is more stable than the second, and which is more stable than the one. Question number 5. The third position is substituted with electron withdrawing groups or minus I groups. If you compare the inductive effect of a nitro group, that is going to be more than that of the fluorine, which is going to be more than that of the OH group. So that way our stability will be the third molecule more stable than the second, which is more stable than the one. In question number 6, in place of methyl, we have 3 bromine, and bromine is exerting minus I effect. So obviously this will be destabilizing the carbocation and the methyl groups will be stabilizing the carbocation. So one will be more stable than 2. In the next question, we have a minus I group over here, and this is obviously methyl, so it is plus I. So this will be exerting a this will be making it more stable. So molecule number 1 will be more stable than molecule number 2. In question number 8, always remember that sp hybridized carbon is more electronegative than sp2, which is going to be more electronegative than sp3. Now if you check the C triple bond N carbon is sp, C double bond NH is sp2, and the CH2NH2 is sp3, and that way if we think more the electron withdrawing power of the carbon, more it will destabilize the carbocation. So the most stable carbocation will be the first one, followed by the second, and followed by the third. Among CH3, CD3 and CT3, here if you want to answer this type of problem, we have to consider the bond lengths. And in that we will notice that CT bond is shorter than CD bond, which is shorter than the CH bond. Now shorter the bond, more will be its electron density in a small area. That means its donation power is more. So when carbon is attached to tritium, it is more stable than when it is attached to deuterium, which will be again more stable than when it is attached to hydrogen. So the stability order will be CT3 greater than CD3 greater than CH3. Now in question number 10, in the second molecule we do not have any electron withdrawing groups, it is a framework of carbon. But in the first molecule we see there is oxygen, which is going to be pulling electron density from both the carbons to which it is attached. So it will be destabilizing the carbocation, and so molecule number 2 will be more stable than molecule number 1. In question number 11, we have been given, so this is CH3. The first molecule is having fluorine, the last molecule is having chlorine, out of which we know that chi of fluorine is greater than chi of Cl. So obviously fluorine will be destabilizing the carbocation more than that of chlorine. That means the carbocation 4 will be more stable than that of 1. Okay. Now out of CH3 and CD3, which is more electron donating, obviously we know CD3 is more electron donating than CH3 because of the shorter CD bonds. That way we will say this is going to be highest stable molecule, followed by number 2, then this will be our third, and this will be our fourth. So the decreasing order of carbocation stability, we will say will be 1, followed by 2, followed by 3, and followed by 4. That should be the decreasing stability order. Next. Now out here we will study a specific rule which is applicable for bridgehead carbocations, and that is known as the Brett's rule. Okay, Bredts, Brett's rule. So, what is the rule? It states that formation of sp2 hybridized carbocation at bridgehead is not possible. And why so? Because of the angle strain. So not only it is applicable for a carbocation but also for carbanion and radicals, or even a double bond. In case of double bond and radical, both the carbons need to be sp2, so sp2, as already mentioned, is not possible. Okay, and why this is not possible? Because of angle strain, as I said. Bond angle strain. So let's take up some problems which are obviously given below. So this is say number 12, in which we can see that electron donation is happening from here and here. So there are two placi effect. Here there is happening from 3, but this is a bridgehead. Hence, this should be the least stable molecule over here. Here donation is happening from one end, whereas in this case it is happening from, the placi effect is acting from 3 ends. Okay, so this is the most stable. So we say this is the most stable, followed by this one, then we have, this is the third, and that will be the fourth. Okay, now let's call this as problem number 13. Out here, electron donation is happening from only one carbon. Here it is happening from 2 ends. Here it is happening from 3 ends. So this will be the most stable. Here it is again, this is, we will say, bridgehead, and hence it is the least stable. Okay, so that being the case, we will say this is the most stable, followed by this one, followed by that one, and the least stable obviously is the last one. Okay, now we are going to study a new topic which will be obviously related to stability of radicals. So what are radicals basically? So let's take the simplest example, say CH3 dot, and we can see if we do a total electron count, okay, or let's say total valence electron count. This is a 7 electron species, so it is electron deficient. It is a odd electron species, and one should expect this to be paramagnetic in nature, and this will also act as a electrophile because it is electron deficient species. Geometry wise, this is planar and the carbon is sp2 hybridized. It looks something like that. And in the p orbital, there should be one odd electron. Okay, that is what a radical is. So it being an electron deficient species, obviously the stability of radical directly proportional to presence of electron donating groups, directly proportional to plus I groups, inversely proportional to minus I groups. Okay, that is what it should be. So let's take some examples. All we need to keep in mind that we have to count from how many carbons there is a plus I effect happening. So here this is from 3, this is from 2, and here this is from 1. So obviously stability of the second molecule will be the most, followed by the first, and at last we will have this one. Again, electron donation is happening from the 3 carbons over here like that. In this case from the 2, and here in this case it is only happening from 1 carbon. So obviously this is most stable, followed by the second one, followed by the last one. In the next case, if we check the chi, then chi of F is greater than Cl, which is greater than Br. Okay, so fluorine when attached to the radical will destabilize it most. Okay, so the most stable one will be the one in which we have a plus I effect, followed by the bromine, followed by the one in which chlorine is attached, and last it will be fluorine. Again over here we can see this group is having plus I effect, where the others are having minus I effect, minus I and minus I. And if we compare the minus I effect, then obviously we will say NO2 is having more minus I effect than that of CN, which is having more minus I effect than that of fluorine. So the molecule in which nitro is attached, it will be the least stable, and which the methyl is attached will be the most stable. So this will be our answer. We know that the minus I effect falls with distance. So with respect to this carbon, we can say this is what? 1, 2, and this is 3 position. This is the 4th position, and this is the 5th position. So that way we can say that as the nitro group moves away from the radical center, its stability should increase. So obviously we will say the last molecule will be more stable than the second, which is going to be more stable than the first. Now if you compare the minus I effect of Nr3 plus and that of CH3, then obviously Nr3 is minus I, whereas CH3 is plus I. Okay. So this will be giving electron density and this will be withdrawing electron density, and that way we will say second molecule will be more stable than the first. Again, if we compare the electronegativity of fluorine, chlorine and bromine, bromine is least electron withdrawing or has the least minus I effect than that of the fluorine. So obviously the stability order will be bromine containing radical more stable, then chlorine, then fluorine. Out here we can see this is a methyl group, so this is having plus I effect, whereas this is minus I, and that too also is minus I, in which minus NF3, there are 3 fluorines. Apart from that, positive charge is there on nitrogen, so obviously we will say this will be having more minus I effect than fluorine. So this will make the molecule least stable. So the most stable will be obviously the one containing the methyl, followed by the fluorine and followed by the plus NF3 molecule. Out here, this carbon is sp3 and that one is also sp3. This one is sp2 and this is sp3. So in that sense we can say the one that is sp2 is more electron withdrawing than the one that is sp3. So over here this will be more stable than the previous one. Out here, the presence of fluorine decreases the stability, and as it moves away the stability increases. Out here there is no fluorine, so this is the most stable, rather it is having plus I effect. So this is number 1, followed by this one which is number 2, and this one being the number 3. Now among the CCl3 group and the phenyl group, the CCl3 is more electron withdrawing because of the presence of the chlorine attached to carbon, and this is rather can be called as group electronegativity. Okay. So as a group, CCl3 is more electron withdrawing than that of the phenyl, and so we will say stability of the first one will be more stable than the last. Again, out here we can see donation happens from 3 such carbons, whereas here only from 1 carbon. So 12 will be more stable than that of the 1. So in this lecture we will be studying stability of carbanions. Okay. So what is a carbanion? Some key points about carbanion. A, it is an 8 electron system, say CH3 minus. The system behaves as nucleophile. It is diamagnetic. The carbon is sp3 hybridized and has pyramidal shape. Unlike as in carbocation or in radical, it was sp2 hybridized. Okay, so it looks like there are two lone pairs present in it, and that should be so. Stability of carboanions directly proportional to minus I groups, inversely proportional to plus I groups, directly proportional to electron withdrawing groups. Okay, so while judging the stability of carbanions given over here in the practice problems, we will look for stability we'll look for electron withdrawing groups, and for destability we'll look for electron donating groups. So as we can see in the first problem itself, there is 3 plus I effect, here there is 2 plus I effect, there is only 1 plus I effect. So obviously the most stable will be the third one, followed by the second, and followed by the fourth. Here there are 3 plus I effect, out here 2 plus I effect, only 1 plus I effect. So this is more stable, followed by second and followed by the first one. Now when fluorine lies in the alpha position, it will exert more electron withdrawing power than from the beta position or from the gamma carbon. So obviously the first one is going to be more stable, then the second, and then the last. Out of CN, the acetylic unit or carboxylic, the minus I effect is in the following order: C triple bond N greater than C O2H followed by C triple bond. So in that sense, we will say most stable is this one, followed by the last one, and the least stable out of the lot will be the one in the middle. In question number 5, among the following carbanions, the electron withdrawing power is NF3 plus greater than NR3 plus, which will be greater than NH3 plus. That being the case, the first molecule will be more stable than the second, which will be more stable than the third. Again, in this case, as the distance of the OH group increases from the carbanion, the stability will decrease because the minus I effect decreases. So this will be the stability order. Here again we can see the electron donation can happen for 3 carbons, here only from 2 and here only from 1. So the most stable will be the one in which donation is less. So that should be the order of stability. in the increasing order. In this also we can see donation can happen from 3 carbon, 2 methyl and 1 carbon chain, and here from only 1 carbon chain. So obviously the one with the less donation will be more stable. Out here this is sp hybridized and this is sp2 hybridized. Electron withdrawing groups or electron withdrawing carbon will make the carbon ion more stable, so this will be more stable than the second one, in which the fluorine has the electron withdrawing effect via sigma bond. So obviously second one will be more stable than the first. In this is sp but this is sp3, so sp carbons are more electron withdrawing than the this is sp2, sorry, than the sp3, and hence sp2 carbon will stabilize more than the sp3 carbon, and hence the stability order will be this. Here the chlorine is lying in the alpha position, whereas in this is alpha, beta, gamma and delta. So in the delta position the chlorine inductive effect is very less, because inductive effect operates only till 3 carbons. So over here we will say when chlorine is joined to the alpha carbon, that will be showing more carbon ion stability than when it is joined to the delta carbon. Out here among NO2 and NF3, obviously NF3 plus is having more minus I effect than NO2, and hence this will be stabilizing the carbon ion more than the NO2. In this compound there is an extra fluorine, and due to the minus I effect of the fluorine or electron withdrawing effect of fluorine, second molecule will be more stable than the first one. Here we can see the CH3 groups are showing plus I effect, and there are 2 of them, which will destabilize the carbon ion as electron donating groups destabilize carbon ion. In number 2 we have 1 chlorine, whereas in number 3 we have 2 chlorine which are withdrawing the electron density from the carbon via the sigma bond, even though they're lying at some distance. But this minus I effect from the 2 chlorine overall will increase the stability of the carbon ion with respect to the second molecule, which again will be more stable than the first molecule. Instead of 2 fluorines, we have 4 fluorines in the second molecule. Larger number of the electron withdrawing groups, larger will be the stability. So second will be more stable than the first. In case of CH3, in question number 17, CH3 is having plus I effect, but this is showing minus I group electronegativity, and this is also showing CF3 minus I group electronegativity. Group electronegativity of CF3 is going to be greater than that of the CCl3. So this is the minus I effect order, and hence we will say CF3 molecule will stabilize the carbon ion more than the CCl3, which will stabilize more than that of the CH3. Electronegativity increases from decreases from sp to sp2 carbon and further to sp3 carbon. So sp carbon will stabilize more than sp2 and then sp3. So negative charge is stabilized by sp carbon more than the sp2 than the sp3. Now out here only one CF3 group is attached, so it stabilizes the carbon ion less than when there are 2 such CF3, and more stability will be attained when there are 3 CF3 groups. So the order of stability is as follows shown.